In the name of God, welcome back. Let's continue with Kinetic Theory of Gases. We have derived some things earlier and used them to make further derivations or predictions based on our theory. I have named them like A, B, C, D, E, F, what we have done so far in that series, starting from Maxwell-Boltzmann distribution, which we called A. We went on and derived the pressure for molecules, that was point G. We have also addressed molecular diffusion, that should have been H. And then point I was mean free path, which we have derived, and then J was viscosity. And the last session was on thermal conductivity, that's K. Today we're going to continue with the last point, L, which is going to be about molecular diffusion. To begin with, let's make some notations clear. So for this we let n star this time be the number of gas molecules per unit volume. Number of gas molecules per unit volume. Okay. And here, if the star is intentional, supposing maybe we have a gas containing different types of molecules, one may want to consider a given type of molecule at a time, and for that given type of molecule we consider n star to be the number of those chosen molecules per unit volume. Okay. So as the molecules move randomly around, one may consider again a layer within the system and try to study how these molecules crosses that layer per unit time, per unit area. So that's going to be a flux, which we have seen before, but here we're discussing diffusion. So the flux is going to be defined in this way, similar to the way we have defined how thermal energy is being transported, or transverse momentum is being transported, that led to the derivation of pressure. Here we define molecular flux, which is phi, let's say we call it phi z. This is going to be equal to minus d partial n star by partial z. Okay, so we kind of consider the situation where if we choose a direction within the gas system, as we move along that direction, let's say it is the z direction, as we move along z, the number of particular molecules under consideration drops down. Okay, so there is some sort of transport of molecules themselves here. When we're talking about diffusion, is some sort of transfer of molecules from one part of the gas system to the other, right? So this constant of coefficient, the constant d, is called the coefficient of diffusion. Okay, so this diffusion coefficient, just call it diffusion. diffusion coefficient. And as usual, the plan is that we're going to use our theory, kinetic theory of gas, which is really based on statistics. We have derived a very nice and important probability distribution, the Maxwell-Boltzmann probability distribution. We're going to use that to derive the molecular flux, phi z, and then from there we can compare with this same equation to kind of derive an expression for the coefficient of diffusion. So now consider a thin slab of gas, let's say with thickness z within the system of gas. We consider two layers. There is an upper layer, and then there is a layer below, and the thickness of the region under consideration, let's say along the z direction, it is dz. Okay, and so one can kind of we should be able to compute like the number of gas molecules, the molecules under consideration inside this region is going to be equal to the area of the slabs layers, and multiplied by the number density multiplied by dz. Right. So we have A times dz sort of is volume. Volume times number density per volume is going to give you the number of molecules inside. Okay? And one can also sort of, we should be able to compute the number of particles per time kind of crossing this lower layer. So they kind of sourcing more particles or molecules in the region under consideration. If we write n in to be number of molecules per time going in, this is going to be equal to the area of the layer times phi z, the flux. So flux is number per unit area per unit time. And similarly, one can compute the number of molecules going out of the slab under consideration. So the number per unit time going out, if we call it n out, this is going to be equal to the area times the difference. So we have phi z minus plus. It's going to be plus. This is z plus partial phi z by partial z times dz. Okay. So it's so the number per unit time going out of the upper layer, one can consider that to be equal to really like equal to the number per unit time coming into the region, so which is A times phi z plus some gradient of the phi z with respect to z. So as we move within the region, we consider that there is some dynamics going on, changing phi of z with respect to the z direction. So if we know what that is, it's phi partial phi z by partial z. If we multiply that by dz, it's going to give us the net kind of the net flux, dynamical flux within the region of interest, and then multiplying that by A is going to give us the additional number of particles per unit time going out of this slab. Okay? And so using these two, we can compute the difference between these two must be the time-dependent changes in the number of particles inside, right? So for some reason, I mean, the system is dynamical. We have number of molecules inside the system is n inside, okay? And this is going to change as we have particles flowing in and particles flowing out, right? How is that going to change? One can compute that if I just simply differentiate n inside with respect to time. So I'm going to have like partial n inside with respect to t. If I differentiate that, this change in the number of particles inside the region or under consideration must be equal to the difference between the number of particles flowing out and the number of particles flowing into the region. Okay, so these two must balance somehow. So this time differential of n inside must be equal to n out minus n in. Okay, so doing the substituting what the quantities, what the n's are in the equation above, we're going to have partial by partial t of a n star dz is going to be equal to the difference between these two. You can do it yourself. It's going to be a partial phi z by partial z times dz. Okay? And from here one can see that partial n star by partial t is going to be equal to minus partial phi z partial z. Okay, so we are having this cancel out, that cancel that, and this cancel that. This gives us this, and then like if we recall that we have defined phi z to be minus d partial n star by partial z. And so this is going to lead to an equation, partial n star by partial t is going to be equal to d times partial squared n star by partial z squared. Okay. This is n star. Okay, and that's it. This is a diffusion equation. In 1D, we have considered 1D scenario. Okay. And so the plan now next is to kind of try to derive an expression for D, the coefficient of diffusion. How do we do that? We remember the definition of flux along the z direction. So flux with respect to some constant z or varying constant z plane. We have done that before, and the expression is something like this. I'm going to write it down again. We have phi of z is number of molecules per unit time per unit area for the whole gas system, and this we can compute to be the integration from 0 to infinity dv and integration from 0 to pi d theta v cos theta and d cos theta, going to have f of v 1/2 sine theta times minus partial n star by partial z times lambda cos theta. Okay. So the expression in the bracket is sort of the number of molecules under consideration transported to have reached some layer under consideration. So this is for a single molecule which is traveling at some angle theta with speed v. Angle theta is with respect to the direction z, and we kind of consider the case where the molecule is reaching like the layer under consideration after traveling a length of the mean free path of the gas, right? So the length it must have traveled along the z direction is going to be lambda times cos theta, right? So if you know lambda times cos theta to be the distance traveled, and if we have a measure of how the number of particles changes with z, which is represented as partial n star by partial z, then multiplying these two will be the net number of molecules per unit volume transported to the layer under consideration. So if we integrate all of that, then we're going to have an expression for the flux. Okay, and this is going to be equal to, doing the integrations, minus 1/3 lambda average speed times partial n star partial z. Okay, and so comparing again the definition, phi z equal to minus d partial n star by partial z would imply that the coefficient of diffusion d is equal to 1/3 lambda mean free path times average speed of the molecule. So you see this is nice. We have an expression for the coefficient of diffusion in terms of the mean free path and average speed. Okay, doing the substitutions for the expressions of the mean free path and the average speed, you can do the substitutions and see that d is going to be 3 pi n d squared times kbt divided by pi m 1 over 2. Okay, so this is using lambda to be 1 over square root of 2 and sigma using sigma to be pi d squared and the average speed to be 8 kbt divided by pi m square root. Okay, so from here one can notice that d is inversely proportional to pressure, since remember we have pressure is n kbt, so we have n here, it's like p, so this is inversely proportional to pressure at constant t. Okay, kbt for t constant, and the coefficient of diffusion is directly proportional to t to power 3 by 2 at constant pressure, and one can kind of derive this coefficient of diffusion times rho. We can check that this is equal to eta, where rho is nm, right? It's like the density, so number density times mass. Okay, that's it for diffusion. You can see we were able to derive an expression for the coefficient of diffusion, right? So what we've done was kind of considering a one-dimensional cartoon of the system under consideration. It's actually easy. One can improve on that to make a 3D, to make a derivation for the three-dimensional case, right? So we can quickly have a look at that. D diffusion equation. In 3D, the total number of particles kind of per unit time flowing out of a closed surface S. So instead of the slab we considered earlier, right? It was a slab with some planes or layers, upper and lower layers in the 1D case. In the 3D case, we're going to consider some arbitrary kind of surface, some arbitrary region. So it's 3D. It's going to have some volume, and this volume is going to be enclosed by some surface, let's say S, right? So in 3D one can consider that it's easy to see, I hope, that n out, number of particles per unit time, kind of crossing the surface of the volume region under consideration. This is going to be some surface integration. So it's integration over S is the surface we are considering, of phi is the flux vector. This time around it's going to be three-dimensional, times ds, okay? The surface area element. Okay? And this must be balanced by the rate of change of the number of particles inside the volume V. So this quantity must be balanced by, so we consider that maybe inside here there is some, let's say n inside and out must be balanced by the rate of change of n inside. N inside, it's also something like you can imagine. It's easy to derive. It's going to be volume integration of the number density of the particles or molecules under consideration times dV. Okay, so number out must be balanced by the rate of change of the number of particles inside the volume V, which is surrounded by the surface S. Okay, so these two must be equal, and this is minus d by dt if we consider that the number of molecules is changing, decreasing, so that's the reason for the minus sign. And we have volume integral n star dv. Okay, i.e. what we're saying is that d by dt volume integral n star dv must be equal to, so the negative sign again, the surface integral of phi times ds. So ds is some element of surface area, and this can be converted, surface integration can be converted to volume integration by using divergence theorem. So this is gradient of phi ds using divergence theorem. Okay, and now we can consider both sides. On the left hand side we have integration, volume integration. On the right hand side we also have volume integration. Sorry, this should be dv. We've converted surface to volume integral dv. So by comparing the right and the left hand side, one can see that we're going to arrive excuse me, we're going to arrive at this relation that minus partial star by partial t is equal to grad of phi, okay, or partial n star by partial t is going to be d using like phi to be equal to minus d grad of n star. So this is the diffusion equation again in 3D. Okay. Just for completeness, we have seen the one-dimensional case. It's something like this: partial n star by partial t is d, partial squared n star by partial z squared. So this 1D, and we have derived the three-dimensional equivalent of it. Right. So diffusion, what we have discussed so far is about the kind of transport of molecules themselves, right? But this diffusion equation can be used for different sort of scenarios, different set of properties of a system under consideration. In general, one can say write partial x by partial t to be equal to d of x. So d is the coefficient of diffusion with respect to x, which is some quantity. I'm going to mention it's Laplace squared x, where, for example, x can be n star. Like for the case of molecular diffusion, we have considered it could be u, which is let's say related to transverse momentum, which is being transported from one point of the system to the other, and it led us to the discussion or derivation for viscosity, an expression for viscosity. X could be temperature, where thermal energy, when we're dealing about diffusion of thermal energy from one point of the system to the other, and so on and so forth, right? So this is sort of general. Remember that for each one of these, the fluxes, for example, phi, for the case of n star, so we're talking about particles or the molecules diffusing, the flux is minus d times n star. So if we take this to be a vector, remember when we were talking about viscosity, some sort of flux was computed. Pi is going to be the coefficient of viscosity times the gradient of u. And the same thing for the case of temperature. We had heat flux, let's say J. It was thermal conductivity times the gradient of temperature, right? So it's a kind of a nice and general equation, diffusion equation. You see it in different places, different parts, and like hopefully in the future we're going to have some sessions to show some examples, or maybe someone else is going to do that, or some AI is going to do that for us. Let's see how it goes. And yeah, one more point to add is that it could be that in the system under consideration we may have some source. So let's say in addition to the non-equilibrium but steady state dynamics of the gas under consideration that leads to some molecules going into a slab and some others going out, one may consider some source here. So let's say the source is just bringing in more molecules, right? Or when we're talking about thermal energy, one can think of say like some thermal energy source, like being pumped into the system, or the reverse, thermal energy could be taken out of the system. For the case of x equal to temperature, one can write, we're going to have partial t, partial temperature with respect to time is equal to d, the coefficient of diffusion, Laplace squared t, which is diffusion, simple diffusion equation we have. But here this time around, let me write the t again. This time around we're considering some source, let's say h. What I want to say is that the diffusion equation can have an extra term on the right hand side if we have a source. So this is for thermal heat transfer in the presence of some source generating, let's say, generating heat at the rate which is given by H per, so generating heat per unit volume, right, per unit volume. And here actually C is heat capacity per unit volume of the system, is kind of dq by dt of the system. So just an additional note to mention that we can have an additional term in the diffusion equation just to show a source term. Okay, I think that's it. We have made beautiful and nice predictions based on our theory. But remember, as a final comment, that our theory was kind of built in a simplified way. We usually consider that molecules in the gas, after collision, velocity of the molecules becomes a random variable again, but in reality this is not true. The velocity after collision is really related to the velocity before collision, so it's not really a completely random variable. Different components of the velocity, let's say V, we have Vx, Vy, Vz, if we consider the Cartesian coordinates, x, y, z. These components were kind of considered uncorrelated and therefore independent random variables. But again, in reality, this is not really true. Another assumption which have been taken is that collisions of the molecules with the walls of their container is completely ignored, and we did not consider rotational and vibrational energy of molecules. These are going to be important, and when if one add these details into the game, the results are going to kind of change a little bit. But the ballpark big picture is that we were able to use mathematics, we're able to use statistics to kind of build a model that can explain physical realities and that can make predictions about, let's say, a system of gas. I hope you enjoy and find this series of lectures on theory, kinetic theory of gas to be useful, and I hope to catch you again on some other series. Goodbye for now.